When you open an app on your phone, type a prompt into an AI interface, and hit enter, the experience feels completely weightless. It is clean, quiet, and instantaneous. We have been trained to think of artificial intelligence as pure software, but the cloud is a physical place. Artificial intelligence is a heavy industrial machine. Every time you generate an image, summarize a document, or ask a chatbot a question, you are sending a signal into a facility that operates on the scale of a heavy manufacturing plant. You are triggering a sequence of events that pulls massive amounts of raw electricity from a local grid, channels it through high-voltage substations, and forces it into dense silicone chips that run hot enough to melt. For the last 20 years, the internet ran on standard data centers. These were essentially warehouse-scale digital filing cabinets. When you streamed a video online, a server simply found the file and sent it to you, using a predictable, steady amount of electrical power. Training and running AI models requires dense clusters of highly specialized chips, known as GPUs. They do not just retrieve files, they actively calculate, working simultaneously to perform billions of complex mathematical operations per second. A standard internet server rack consumes 5 to 10 kilowatts. A modern AI GPU rack consumes over 100 kilowatts. Scaled up, one row of AI cabinets equals an entire suburban neighborhood. A full data center demands the continuous draw of a mid-sized city. Plugging these servers directly into a standard municipal power grid would act like a massive short circuit. To avoid destabilizing local electrical infrastructure, modern AI relies on its own backstage utility ecosystem. Before the electricity ever reaches a computer, it must be intercepted. High-voltage power arriving directly from the regional transmission grid enters a dedicated substation, where massive steel transformers and heavy switchgear step it down to a usable level. But raw grid power is dirty, constantly fluctuating with fractional voltage drops and microsurges. While unnoticeable at home, AI clusters are incredibly sensitive. A drop of even a few milliseconds causes calculations to fail. The system crashes and millions are lost instantly. Raw electricity is far too volatile for these machines. The facility requires an intermediate layer dedicated to cleaning the power before it reaches a chip. The power flows into fortified rooms filled with uninterruptible power supply systems. These are thousands of heavy-duty industrial batteries wired together into a massive array. These batteries act as giant electrical shock absorbers. The computers draw their power purely from the batteries, receiving a perfect, unbroken, digitally clean wave of electricity that is insulated from grid flickers. If the main municipal grid fails completely, these battery arrays provide exactly enough time for a final layer of descents to engage. Hidden behind the building is an armada of combustion engines, often the size of shipping containers. Within seconds of a blackout, these massive generators roar to life, and the facility physically disconnects from the outside world. Maintaining AI uptime requires transforming a data center into a self-sustaining off-grid power plant. The megawatts of raw power pouring into the building eventually convert into a single thing: extreme heat. This is a consequence of the first law of thermodynamics. Energy cannot be destroyed. Computer chips work by flipping microscopic electrical switches billions of a second. Every flip creates friction and thermal energy. Multiply that by millions of chips running at maximum capacity, and heat generation becomes a severe industrial hazard. Machines left unchecked will experience thermal throttling, slowing down to avoid self-destruction. Within minutes, the chips would reach temperatures hot enough to melt their own solder and burn out the hardware. For decades, data centers managed heat like giant refrigerators. Massive industrial air handlers pushed freezing cold air up through the server racks to capture the heat and exhaust it out the roof. Air is thin and inefficient. For the densest AI racks drawing over 100 kilowatts, air cooling cannot remove the heat fast enough. You could blow a hurricane of freezing air at the chips, and they would still overheat. This has forced a shift in the architecture of the internet. To prevent the hardware from melting, modern AI facilities use a complex system called direct-to-chip liquid cooling. Inside the server racks, a microscopic plumbing system runs right alongside the electrical wires. Chilled fluids are pumped through tiny microtubes directly into metal cold plates that sit flush against the naked silicon. The fluid absorbs the extreme heat off the chip and is pumped away in a continuous high-pressure loop. In high-density setups, engineers bypass the tubes entirely. The entire server motherboard, wires, chips, and all, is physically submerged into a vat of non-conductive dielectric fluid. As the chips generate heat, the dielectric fluid physically boils around them. The boiling bubbles carry the thermal energy to the surface of the tank, where it condenses against a cooling coil and falls back down in a permanent self-contained rainstorm. The hot fluid is pumped out of the server rooms through thick industrial pipes and pushed into massive external cooling towers, where evaporation and giant fans release the heat into the atmosphere. Every piece of this physical environment is designed around the rapid flow of extreme power in and extreme heat out. Modern AI facilities are heavy industrial thermodynamics engines. This infrastructure has grown too massive and power-hungry to be built in dense cities. There is not enough physical space or electrical capacity left on municipal grids. Instead, these massive, windowless, brutalist structures are migrating away from urban centers and into rural landscapes. They are anchoring themselves directly next to heavy industrial utilities, next to hydroelectric dams and nuclear power plants, where raw power and water are abundant. The digital world is physically reshaping global geography to chase industrial resources. The front stage of this system is designed to feel like magic. You ask a question, and a conversational answer appears on your smartphone screen a second later. Hitting enter on an AI prompt opens a physical valve. You are engaging a sequence of industrial hardware. A single prompt pulls raw grid power, spins up industrial electrical infrastructure, forces liquid through metal cold plates, and fires massive cooling towers miles away. Behind the frictionless illusion of your smartphone, you are the direct operator of an invisible, world-spanning heavy metal machine.